Okay, now welcome in this exercise lecture. And again, before discussing several MCQs, I would like to recall the several definitions and results which we have already studied. So, first is the sequentially compact set. So, sequentially compact set means first we call that is the Bolzano-Weierstrass property. So, a metric space X is said to satisfy the Bolzano-Weierstrass property if every finite subset of X has a limit point. And then we have proved that basically, and then we have a sequentially compact. So, every sequence in X has a convergent subsequence. So, Bolzano-Weierstrass property, sequentially compactness and compactness. We have proved that all these three concepts are equivalent in the metric spaces. So, compact set means every open cover of X has a finite subcover, then it is called compact. Okay, and sequentially compact means every sequence has a convergent subsequence. And for the Bolzano-Weierstrass property, that every infinite subset of X has a limit point. Okay, so and then we have proved that these three results are equivalent, and we have seen several other properties, and we also proved that a compact subset of a metric space is closed and bounded, but the converse is not true in general. So, where we have given several exercises, and then we gave the totally bounded. So, totally bounded means that it has an epsilon net, and then we proved that if sequentially compact metric space is totally bounded and complete. Okay, so this you keep in your mind, and then the converse is here we have every totally bounded complete metric space is sequentially compact, and then it is compact. So, only totally bounded space need not be sequentially compact, or only completeness is not sufficient to say that a space is compact or sequentially compact, but it should be totally bounded and complete, then the space is sequentially compact. Okay, and then every totally bounded metric space is separable. This we have proved, and then we have finally we proved that every sequentially compact metric space is compact, and so we had this kind of result which says that the compactness, okay, sequentially compactness implies the compactness by using this theorem, and the compactness implies Bolzano-Weierstrass property, and sequentially compactness is equivalent to Bolzano-Weierstrass property. So, this we have seen in our previous talk. Okay, so let us see here is some MCQs. Okay, so here is I have some MCQs for the metric complete metric space. Let suppose if every subset of a metric space is compact, every subset of a metric space is compact, then X is finite, X is infinite, cannot say whether X is finite or infinite, none of the above. And you see that just we have seen that if every subset of a metric space X is compact, then the space is compact, then the space is finite. Just we have seen this in my previous talk, and therefore the answer of this is your A. Okay, now let us take the question number 2. Question number 2 is said that every compact subset of a discrete metric space X is finite, infinite, countable, or none of the above. So every compact subset of a discrete metric space X. Okay. Now you see here is if you have in the discrete metric space, singleton sets are open sets. So you can form a open covering of the set, but it would have a finite subcover only if the set is finite. So every compact subset of a discrete metric space is finite. So the answer is A. Okay. Now take the question number . Under the usual matrix, which of the following is true? R minus 0 is compact. As in my previous talk, I have mentioned that R minus 0 is not compact. Okay. Why it is not compact? Because you have seen that you can take R minus 0. R minus 0 means you take minus infinity to 0, open interval, and open interval 0 to infinity. And in the real line R, okay, a set is compact if and only if it is closed and bounded. But this set is not closed. Okay, this is not a closed set, and therefore R minus 0 is not compact. So this is very clear that the first one is not true. Okay, so first one is not true. Actually, here is we have connected. Okay, so R minus 0 is also not connected. Okay, and R square minus 2 is compact. Okay, just we have proved that it is not compact. In the exercise, in the previous talk, we have seen that R minus R square minus 0, 0. If you if you take XX, so we have in the exercise we have proved that if you have this R square minus diagonal element XX, it is not compact. Okay, so instead of taking you can take you can take x is equal to 0 and y is equal to 0, only one point, so it is not compact. But you know that this is your connected set. So this is R square minus 0, 0 is a connected set. But this R square minus 0, 0 is not compact, R minus 0 is not compact, and it is not connected. Okay. So this is the result. Now next MCQ. Next MCQ says that which of the following statement holds? Which of the following statement hold? Every totally bounded metric space is compact. As I mentioned that every totally bounded metric space is not compact. You need to add some condition. Okay. What was the condition? You can see that we proved that here is every totally bounded complete metric space is sequentially compact. And we know that sequentially compact metric space is compact. So every totally bounded complete metric space is compact. Not the every bounded metric space is compact, and also not only complete metric space is compact. You have to add the condition totally bounded plus completeness. So here you can see that, but the converse, you keep in mind, for the converse, you can see that sequentially compact metric space is totally bounded and complete. Okay. A sequentially metric space is totally bounded and complete. But both this plus this implies this, but not only one. So this you keep in mind, and with this one, these results, we will have this our MCQ. We say that every totally bounded metric space is compact. No, it is not true. Every complete metric space is compact. No, it is not true. Okay, but compact metric space is complete. This is true. So, and then the next is every totally bounded complete metric space is compact. So, C is true. So, C is the answer of this question. Okay. Now, take next exercise, next MCQ. Let XD be a metric space. Which of the following is not equivalent to other? Which of the following is not equivalent to other? We have seen that X is compact. Okay, if and only if X is sequentially compact. If and only if X satisfies the Bolzano-Weierstrass property. So these three are equivalent. But again, as I have mentioned that the X is totally bounded. Okay, it does not imply the compactness of X. Okay, just I have mentioned the result. We say that a totally bonded plus complete implies X is sequentially compact, and sequentially compact is equivalent to the compactness, and therefore this D statement, D is totally bounded, is not equivalent to A, B, C. However, A, B, C are equivalent, as we have proved that a compact space is sequentially compact, and a sequentially compact space satisfies the Bolzano-Weierstrass property, and if a space satisfies Bolzano-Weierstrass property, then it is compact. So, the answer is here is your D. Now, consider next exercise. So, the next exercise is that consider the following statements. The first is set of integers with the usual metric is not a compact metric space. The set of integers with the usual metric space is not a compact metric space. Okay. Second is, so this is true or not? The set of integers with usual metric is not a compact metric space. This we have proved in the exercise, not in the exercise, in the examples. Okay. Then X consisting the 0 and this set, okay, 1, 1 over 2, 1 over 3 and so on. This set is compact subset of R. This we have proved, this set is compact, but if you remove 0 from this set, then this set is not compact with the usual metric space, with the usual metric on R. But if you include 0, then it is a complete metric space. And in the exercise, we have already proved that if you have, you take a set and include the limit point of all the sequences in this set, then the set is compact. Okay, so this set is compact. And now the open sphere with center at origin and radius 1 is not compact. Yes, this is true. The open sphere is not compact. Okay, this we have already studied in my previous talks. Then the open sphere is not compact. And next is that let XD be a discrete metric space and X is an infinite set. Okay, then X is not compact. Yes, it is not compact because if X is a discrete metric space, okay, and X, then X can be compact only if it is finite. But here is x is infinite, so this is not, so x is not compact. So it means that all four statements holds good. It means that which of the following is true? A and B, but not C and D? No, because all holds. So we can say that the A, B, C, D all are true statement. Okay, let's take here is which of the following statement is true? Let's take what are the statement. Statement is under the usual metric dxy is equal to mod of x1. The real line is neither bounded nor totally bounded. Yes, the real line is neither bounded nor totally bounded, as we have seen in my previous talk. The metric space under the metric D star, which is equal to minimum of mod of x minus y and 1. The real line R is bounded, okay, but not totally bounded. Okay, so this is bounded, but it is so this is the minimum of this one. Okay, so first you see that the real line is not bounded. Okay, real line is bounded. If the minimum is equal to this one, which is less than 1, then this is in both cases, if you are taking this is equal to this, then D star, the R with respect to D star is bounded. But here it is not bounded, so this is not true. Because if you have the real line, but the real line with respect to the this mod or with the usual metric dxy, okay, so instead of this D star you can write as D star, you can write as D star xy is equal to minimum of 1 and dxy. But in the usual metric space, it is equal to x minus y. So if you take then with the R with respect to this metric is not bounded, but with respect to this metric it is bounded. So here is we can say that this is not true, B is not true. The second one is under the usual metric dxy is equal to this. The real line R is bounded. No, it is not true. Okay. With real line, here is neither bounded nor totally bounded. This is not totally bounded. And with respect to this, the real line is totally bounded. No, this is also not true. So the answer is 1. The usual metric space R with the usual metric is neither bounded nor totally bounded. So the answer is A. Now take another MCQ. Under the usual metric on R, which of the following sets are compact? Okay, so let's say here is because this is your closed set and bounded, this is your closed and bounded, so the whole set is closed and bounded subset of R. So closed and bounded subset of R is compact, so A is compact. Okay, which of the following sets are compact? So A is compact. Okay, then here is this is greater than or equal to 0. So but this is not bounded. This set is bounded below, but it is not upper bound. Okay, so here is you see that this is not bounded, but it is closed. It is closed, but not bounded, and therefore this is not compact. Now we take all the irrational numbers between 0 and 1. Okay, this the rational numbers between 0 and 1. This is bounded but not closed. This is bounded but not closed, and the D, this is bounded, okay, and it is closed because the limit point of this set is 0, okay, which is in A, and therefore A is closed and bounded, okay, and therefore it is compact. So A and D are compact and the B and C are not. Okay, so take a next example MCQ. Under the usual metric on R2, which of the following statements are correct? Which of the statements are compact? Which of the following sets are compact? So here you have this one. Okay, so this set is compact. Basically, it is not closed because you are considering only y is equal to 0. Okay, so y is equal to 0. Only this y is equal to 0. So if you take a point, it is the center of some operation. No, so this is not closed. And if you take this set is closed, okay, this set is closed, but here is it is also bounded, but this set is from the other. So this is not a closed set, but this set whole set is not closed set. This is the boundary. Okay, this is the boundary of a set. Okay, so this set is closed and bounded, and this set is closed and bounded. Okay, so both the C and D are true. So these two sets are closed and bounded, and therefore they are compact, but other are not. Okay, so finally take the last MCQ. So let X be a compact metric space. Which of the following statements are true? So X, you take the diagonal element. Okay, remove the diagonal element, is removed. Is compact? It is not compact, as we have seen. Okay, the diagonal remove the is not compact. Yes, this is correct. So B is correct. Then this, the whole space is compact. No, this answer must be which of the following statements are true. So this is not compact. Remove, this is not compact. So B and it should be B and D. X is compact. No, X is B and C. So X cross X. If X is compact, then X cross X is compact. Okay. So this is so B and C. They are true. So B and C means B and C. So B is true. So B is true. So this is true. So here is that is the end of these MCQs related to the compact spaces, and in other lectures we will also see some more MCQs and exercises related to the other exercises, other chapters. So thank you very much.